The cross product in the formula above is what tells us the charge has to have a velocity component perpendicular to the field for there to be any force on it. The direction is found the way you do all cross products, and that's the right-hand rule. This is the first of several of them we'll see this semester. Take the fingers of your right hand, point them in the direction of the velocity, curl them, make a fist into the direction of B, and then when you're done, the thumb points in the direction of the force. Of course, if you're dealing with a negative charge, that's going to change the direction of the force by 180 degrees. So, to do some examples, here, start off pointing the fingers of your right hand down, and then curl them to your right. Your thumb will be pointing towards you. That's what this little F is. The circle with the dot in it means an arrow coming out of the board or screen towards you. What about this one? We start off with the charge coming towards you and the B field pointing towards the ceiling. To do this one, hold your hand, and it'll help if you face your palm towards the ceiling. You've got your right hand fingers pointing towards your face, curl them up towards the ceiling in the direction of the B field. Your thumb will be pointing to the left. So that's the direction of the force on a positive charge. You can look in the book or online or any physics book and you'll see many more examples of this. Now, we talked about the fact that electric field lines start and end on charges, but magnetic field lines are loops. The reason for this difference is there are no what are called magnetic monopoles in nature. A monopole is an isolated North Pole or South Pole. There are electric monopoles, just regular positive charges or negative charges would be monopoles. There are some theoretical reasons to believe that there may be magnetic monopoles somewhere in the universe, but no one has successfully repeated a discovery of them so far. So as far as we're concerned, they only come in pairs. If you cut a magnet in half to try and get a north and south pole, you actually get two more north and south poles. So you've got a north-south touching each other. So it doesn't matter how you try and cut it, you can't cut it into separate poles. So we say that the field lines are directed away from the North Pole, but they don't originate there, and they're directed towards the South Pole, but they don't terminate there. So now, knowing this, what if we have a charged particle that moves from a region where B equals 0 to a region where B is not 0? So we have this in this figure here. On the bottom of the dotted line, there's no magnetic field, and on the top, there's one coming out of the page. What we would find is, below the dotted line, before the charge crosses it, there's no force on it. Once it does cross over, though, you should point your fingers up the page, then curl them to come out of the page, which is going to leave your right thumb pointing to the right. So you get a force like this. As the force pushes on this moving charge, it's going to turn it to the right. And eventually, if there's a uniform magnetic field, so it's the same everywhere above this dotted line, eventually it's going to send this right back out. So this works as kind of a reflector. We fire this charge in at some velocity, and it makes a 180 and comes back out at the same velocity. Now, since the force is always perpendicular to the velocity, if we had a magnetic field everywhere and we fire this charge into it, what we would notice is the charge wouldn't just turn around 180, it would make a complete circle. It would continue looping around, same circle forever. We know from last semester that if something is going to be moving in a circle, it's going to have an acceleration that's v squared over r, so the force on it has to be mv squared over r. The only force we have is this force on a moving charge, also called the Lorentz force, qvB sine theta. So we know that our only applied force has to equal mv squared over r. Now, if b is perpendicular to v, sine of theta is 1, and we can ignore it. So we have qvB equals mv squared over r. We can cancel a v. And we can write that the size of the circle that this charge will make is mv over qb. Go back and think about this and see that a positive charge moving here is always going to get turned to its right, whichever way it's moving. If the field is out of the page, the charge gets pushed to its own right side. We could ask what work is done by this force. We know that the work is a dot product of force and displacement, so we could say it's power times time. Power is force dot velocity. And our magnetic force is qv cross b. So we can write this as qv cross b, and then the product of that times v again, dotted into v again, multiplied by delta t. However, what we notice here, we know that in a cross product, the result of this has to be perpendicular to both initial vectors. So F, which is qv cross b, has to be perpendicular to both v and b. Now, if we take something that's perpendicular to v and we get the dot product with v, that's by definition going to be 0. Anything perpendicular to v dotted into v will give us 0. So that tells us we don't get any work done by this magnetic field. Now, could we turn this into a tricky test problem to see that you're watching for this? I've done it before, so let's go over what I've asked before. Let's say we have a 2 nanocoulomb charge moving to the west at 300 meters per second through a magnetic field of 1.75 Tesla, which is directed up. What's the magnitude and direction of the force? Well, it's a positive charge. I'm going to take my right hand, point it to the west, and then curl it up. And we know that our only choices for directions perpendicular to both west and up, V and B, are north and south. So it's either going to be moving to the north or moving to the south. When you point your fingers to the west and curl them up, your thumb is pointing to the north. So that's the direction of the force. The magnitude is Q, V, B, sine of 90. We get 1.05 times 10 to the negative 6 newtons. Then I could give you the mass of the particle and say, well, what's the acceleration? That's an easy problem from last semester. Acceleration is F over m, so we get 21 meters per second squared. Another problem from last semester, I could say, what's the kinetic energy at the start of the problem? It's just 1/2 mv squared. So you calculate that. Then I could say, okay, the acceleration is constant in magnitude. What's the particle's velocity after 10 seconds, and what's its kinetic energy? Now, this is where you would end up making a mistake if you're not being careful. The first thing that will probably pop into your mind is, well, let's do the kinematic equations, because acceleration is constant, and I want to find the connection between initial and final velocity and time. So you might say, let's do this. So I'd say 300 meters per second, and then 21 meters per second squared times 10 seconds. I get 510 meters per second. But the problem is the acceleration is perpendicular to v, so it can't change the size of it. It can only change the direction. So our final speed and our initial speed are exactly the same. Now, this didn't come up in the chapter where you first looked at kinematic equations because you were looking at 1D motion and you don't have the idea of perpendicular in 1D. So the real answer would be the kinetic energy at the end is exactly what it was at the beginning. Now, there's something else interesting we can do with this kind of setup, and we'll talk about that next.